is class 12 in ME470, and we're talking about ball bearings for the third class. This time we're going to take the equivalent radial load when we have varying loads. This is very much related to what we did in ME370 in Chapter 6 with fatigue, when we have the basic type of loading that we will often assume initially is that it's consistent and always constant. Well, not constant, but the pattern is constant, right? But then we learned when we got into the later part of Chapter 6 that we might have scenarios other than that, and we'd want to compensate for it, right? So that we might have, I used to make will make the analogy of the Mustang that I want to buy, and where I want to get a Mustang that was driven by someone that really carefully, like the little old lady who only took it out on Sundays, and then when I get a hold of it, it's really going to be I'm going to put a lot more damage, accumulated damage on it, because I'm going to drive it a lot harder than the little old lady did. So that's two different events. But we could also have a scenario where we have lots of different events, right? Where this car is going to pass through a lot of people's different hands. They're going to operate it differently. So if we want to try to estimate what the life of the thing is, we need to make adjustments for that. And basically, this is another apples to apples type of pursuit that we're making here, right? So the stresses don't always fluctuate the same amount. So the two things that we did initially was to use Miner's rule and Manson's method, if you recall, right? And then after that, we did something called cycle counting, and we used the raindrop method, right, where we had these raindrops that would fall down, and we would see that we would be able to count, and we would look for these hidden fluctuations inside the events that were taking place, right? So hopefully you'll recall some of this. If not, you'll see what we're going to, the similarities, whatever. Okay, so I'm going to try to refresh your memory of Miner's rule here. So let's take a look at the camera here. Okay, so you remember that the idea of Miner's rule is that we have accumulated damage, and so we have like this damage fraction idea, where we have the number of cycles divided by the number of possible cycles, right? So this right here is going to be the life at a particular loading. And so we're like, for the most simple one, where we just have two loading scenarios, right? So the first loading scenario is like a stress of, let's say, sigma 1, and that's done for n1 number of cycles and can live in capital N1 amount of life, right? Where we might have sigma 2 was done for little n2 number of cycles right there. And you want to say, oh, well, maybe we know this and we want to find that, right? Well, what we do is we get capital N1, right? That's going to be the amount of life that we could expect at this stress, right? So if we just always use this stress, we're predicting it will fail at this time. We also use this capital N2, and so now that's the life if we only used this stress, how much long it's going to live. But we already used up some of these cycles, so we want to find out how many of these we're going to be able to get after we've accumulated this number of cycles, right? So this is the idea, is we have this damage fraction is going to equal 1. So N1 over capital N1 plus little n2 over capital N2 is going to equal 1. So this is the damage fraction. It's the fraction that we've used up of the life. And then we're going to say, well, okay, so if we want to find out how many cycles this thing's going to live, we found out how many it could have lived if it only experienced stress 2 right here. So that's the idea of Miner's rule. And you might recall that, like, graphically, what that ended up being was let's see if I'm going to say this the right way. It was going to be like having a parallel line, if you recall, right? That we would have, we take the line and we make it parallel down. So what we will find if at a particular stress right here, we'll say that, well, we should say that first right here. How we draw the line, if you recall. If like we say that this is, let's say that this is stress 1 right here, right? And here is your capital N that you would have onto the thing. This would be N1 if this is stress 1, right? But if you now if you only use it, say like this number of cycles right here, if this is like N1 right here, what we could say now is, well, we could take this and subtract out that from it and get like this right here, right? So this little point right here, and this is not a linear scale, so you got to watch out, because so I'm just making an example. This is N1 minus N1 right here, this length right to there. You say this is its new life line, and it's parallel to this, right? So this is what it was graphically. And then you would also say right here, this is the new endurance strength that it would have, right? So it has a new endurance strength. Oh, this is not prime, but we would say it's like 1, right? That would be like the one that's after event 1. Now, if you start subjecting it to a new stress, like I don't know if we want to use one that's down here, we could have say, okay, here is someone who's going to use it at a lower stress. Here's what we're going to predict the new life is going to be. This is what we're going to say how many it's going to use, right? Or maybe another way. Let's do a high version right here. So let's say that this is sigma 2 up here, right? Right here would be what our little n was going to be. That's what we're going to predict. Little n 2. That it could live them out. But now notice right up here, by the way, that this would be big N2, right? So here's where we would calculate the thing. This is what's actually what we would graphically take a look at to try to understand the consequences of this. And really, we did this in many ways. We did the graphical method to try to explain the Manson method. Right. So I just wanted to refresh your memory in case you hadn't seen this before as well, but also it's an important thing in terms conceptually. But the big topic that we're talking about here is condition monitoring, and this is something that goes on monitoring. This goes on in industries all the time. It goes going on in your car right now. The topic of condition monitoring. Right? Your car is trying to evaluate its condition in terms of and tell you when it needs maintenance. Well, trying to predict when something is going to fail is a really, really important engineering category of things. We call that condition monitoring. It's especially people are especially interested when it comes to wind turbines, because there's like, once you pay the for buying the wind turbine, it's like free energy, right? All you need, you have the initial investment, but now the energy, you're just pulling in energy, which is money, right? Except that you have to do maintenance onto the wind turbine. So if you want to maximize your profit there, you want to minimize your maintenance. So you really want to only do maintenance when you have to do it, right? And you don't want to do it after there's been catastrophic failure. So you have to do some type of condition monitoring. Well, there's a lot of money to be made in trying to figure out ways to be able to like predict when something's going to fail by way of observing the taking vibration meathements, doing testing oil, that type of thing, and having any kind of little indications that the thing is degrading in performance and will need to have maintenance soon. Well, by way of like counting cycles and being much more sophisticated stuff, we're able to do a better job of trying to evaluate the condition of a piece of equipment. So it's kind of an important type of category of things. Now, the same concept as Miner's rule, and this is all ME470 review stuff right here, of the damage fraction. We have something in bearing life that we also can do, right? So as a similar thing of that damage fraction, we have we apply that same idea that we were using for evaluating life in a bearing, right? We equated the manufacturer's conditions with our conditions based on that scale right here, where we had the log of F right here, and we had the log of life, and we had dot, 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 and they drew a line through it, and they saw that it had, in essence, a slope of A in a log-log scale, right? So that's what we have right here. We're using that concept here. But now we're going to, let me pause this for a second here. Okay, so now what we're really doing is you notice they took the log off of this part of the scale, whereas this, and they raised this one to the F over A, so it's not the same graph as this right here, but we are graphing force versus life. The hypothesis is the damage hypothesis, instead of the damage fraction that we were thinking of before. We're going to say that this area right here represents damage, right? So we have like this, we're writing out this right here. So if we want to have an equivalent amount of force, what we do is, if we have a whole bunch of different events taking place, like let's say we have, this is the cycle of things that are happening right here. It's getting loads. This load is this much of a load and this much of a load. You notice they're all raised to the A as part of that. Well, if we get the area of all of these, right, and then we divide it through by the length that we have of these, we can have an equivalent amount of force right here. So the equivalent load can be found by taking the area of all of these events. So here you go, here's your damage. We're going to say for a particular amount of damage, and then this is really just arbitrary right here. We set up each of these events, right? Here's the area for this one, the area for this one, the area for this one. And we say, well, if you have those lengths right here, this total length right here, and you could multiply it by an equivalent one. So if you want to find the equivalent one, you just add all of these up, divide through by here, and then take over here. So another way that we can write this is equation 1113, okay, which is written either, well, it's written this way right here. We have the sigma of all these little f's right here, I, it's a little fi, times ei right here to the a. I don't know why they always do the e in there, but I don't think you could just think of them as each individual loading thing, right? Okay, and so this is the every event right here, and where that little f is going to be equal to li divided by the sum of all the little li's, and this is referred to, this thing right here is referred to as the turn fraction. And by the way, it doesn't have to be, as long as it's like a ratio of things, it could be, it doesn't necessarily have to be like time. I mean, it could be time, or so the percentage of time. It could be number of turns, is the idea right here, is this turn fraction, and that kind of thing, as long as you're comparing apples to apples. So we're doing another apples to apples type of pursuit here. So do I want to do the example that's right in the next example? Sure. No, let me make a second. Let me continue in a new video right here, because I think this one's long enough, and I don't think anyone's going to listen to it anyway.